The definition of instantaneous velocity of a particle, according to Paul Allen Typeter, was already mentioned in a previous video in the series Images of the Universe. It is always useful to abstract from the topic with the support of science, so let's remember the concept. At first sight, defining the instantaneous velocity of a particle at a given instant seems impossible. At any given time, a particle is located at a specific point. If it's positioned at one point, how could it move? If it's not moving, how could it have speed? This paradox is resolved if we remember that, in order to observe and define a movement, it is necessary to look at the object's position for more than one time. Analyzing this quote closely, some conclusions can be drawn about the behavior of particles. One of them is that its movement depends on the existence of any time interval. Without time, they would remain static and could not have their presence revealed. When you think of a particle as an electron, it will never register in its steady state, which would ultimately be its natural state. It's just that we need to light the electron so that it can go under relative motion and thus have its presence revealed. The photon energy used to assess the particle's position or velocity is purely kinetic. That is, the photon is never stationary. When you light an electron, the light disturbs its position or its speed in an exclusive way, creating uncertainty. This creates an exclusion principle of direct access to the particle. Even though it is immobile in the real plane of the universe, you can only see it as long as it is in continuous motion. For example, when a quantum collides with a free electron on a metal plate, both appear simultaneously. Until today, it has not been possible to measure any time interval that could separate them. So much so, that when a particle can be observed by the light it scatters, it is called a photoelectron. It is not by chance that the photon is described as a particle with zero rest mass, as its energy is purely kinetic. As the particle in motion cannot be dissociated from the light it emits or reflects, the space surrounding the particle is also described indirectly. The behavior of scattered light merges with the behavior of space itself, resulting in the formation of a false continuum in apparent motion. This would have led us to compare the behavior of space with that of an elastic band or that of a spring, models that are normally used to describe the simple harmonic motion of light. We would need to keep in mind that for us, a particle only exists while illuminated. This is what allows it to be seen indirectly and in continuous motion. It also allows explaining how the same particle could be in more than one place at the same time. Every lit particle would have a dark companion, which, in this case, would be itself. The particle's necessary illumination would hide its true condition of being stationary and timeless in its origin. As space would be out of the process, the apparent movement depends on time. That is, the relative motion of the particle would be in time and not in space. The importance of the observer's point of view was enshrined in the Copenhagen interpretation. According to Bohr, quantum reality would remain obscure until it was finally observed. For Halliday and Resnick, a hydrogen atom would only exist in its steady state, in which it would not radiate any light. Note that this problem could be linked to our dependence on the particle's illumination and the existence of any module of time, which could be measured indirectly by the limited speed of this light. In order for the particle to enter in motion, it would be necessary to know the position it would occupy in more than one time. That is, the relative motion of the illuminated particle would ultimately depend on our temporal memory. As the quantization or the packaging of light would not demand any module of time that could be measured directly, this would attribute discontinuity characteristics to the space-time continuum if, as everything indicates, it was indirectly described by light. This would happen with the brightness of all the stars we observe at night. It is very difficult for us to conceive of the possibility that our memory could act discontinuously. Sounds like something out of science fiction. This confusion between the behavior of light and space was created by the emergence of quantum mechanics and its uncertainty principle. People are not aware of the unfolding of the quantum hypothesis and go on with their normal lives. Everything seems very far away, taking place in a microscopic world that seems to be dissociated from the physical reality we observe. It is believed that the laws that would act in the microscopic universe would not be applicable on the astronomical scale. However, when it comes to our point of view, infinities become equal at all levels of matter. Our observation makes the subatomic and macrostructure worlds become one and the same, since, to be observed, these two levels of matter would depend on the same form of remote tracking of light. Your telescope would be useless if the light from the distant stars were no longer available to you next to your observation post. The same would happen with the observation of electrons. As the observer depends on the local scattering of the light, in both cases, it would not matter the module of time that the light might have needed to travel through space at a time prior to its scattering. It is believed that from the point of view of someone moving at the speed of light, time should stop. That is, this time would tend to zero when the displacement of light would tend to be instantaneous. It is not known whether this would also occur on the astronomical scale, but, in the case of subatomic particles, the opposite would occur. They would tend to immobility when time tends to zero. The instantaneity of light would be dictated by time, not by its speed in space. Even if the subatomic tendency of time contraction remains suspended to infinity, aiming to preserve the uncertainty principle, it is clear that the speed of light would have been incubated at that level of matter and before the manifestation of time. It would be part of an information package opened outside its own time. This fits with the necessary timeless phase of light quantization. For our memory to be preserved, as well as the uncertainty of the particle's position, time could never contract to absolute zero. Its measurable minimum limits, in this case, would establish an insurmountable barrier for the operator of the quantum system. Beyond that barrier, there would be no measurable time and no movement. There, the universe would become virtually stationary. The quantization of energy, or its packaging, would act in a similar way. That is, it would also create a barrier for the performance of our memory, as the formation of the quantum does not demand measurable time. No time, no memory. Subatomic particles cease to exist because they cannot be remembered. There must be many of them in these conditions. For, although they are there, we do not have wavelengths short enough to illuminate them and reveal the positions they would occupy in more than one time. With the exclusion of direct recording of this phase of formation of the photon of light, which will later be scattered by the particle, the operator of the quantum system will see the particle being replaced by its image that shifted in time. The scattered photon would act as a messenger of space, and the particle itself, leaving space out of the process. If space could be accessed directly, there would be no uncertainty in the particle's position or velocity. Since the photon would have zero rest mass, it will always arise, for us, in continuous motion, composing the particle nature of light. Due to the timeless nature of the quantization phase, the absolute displacement of light in space cannot be demonstrated. Thus, the particles themselves, when observed in relative motion, would result from transitory condensations of energy. Sometimes they will be there, sometimes not.